Delete in binary search tree. How can you delete a node from a binary search tree? This process of deletion is slightly tricky if you compare it with the processes of insertion or search in a binary search tree. The reason for this trickiness is that there are three different subcases of deletion, and all these three different subcases, they are to be dealt in different methods. Let us first see what are the three different subcases of deletion, and then we'll understand how do you deal with each of those. The first subcase is that you want to delete a leaf node, that is a node with no children or zero children. Second subcase is that you may want to delete a node which is having one child. And the third subcase is that you may want to delete a node which is having both left and right children. So two children. These are the three different subcases. Let us see how can you deal with each of those. Consider this is your binary search tree. Let us have one child here and two children here. This is your binary search tree. In this binary search tree, if you want to delete a leaf node, that is a node with no children, this node is a leaf node, this is a leaf node, this is also a leaf node. If you want to delete any of these, it is easy because there are no dependencies. Whenever there are children, there will be dependencies on that node. Whenever there are no children, you can simply delete the node off. It won't affect the tree at all. So if this is the node you want to delete, you can simply remove this node off. It won't affect the remaining binary search tree. So this is the easiest case when you want to delete a leaf. What if you want to delete a node which is having one child? If this is the case, then let us say here one child is present and you want to delete this node. In this case, you can't simply delete this node off because then the remaining part of the tree which is dependent on this node, that will also be gone off. But you don't want that. You want this node to stay, but you only want the node with one child, this node only to be deleted. How can you do this? First thing you have to think is, you have to relocate the node which is the child of the node to be deleted to somewhere else, because that should be part of the main root, but it cannot be attached to this node anymore because you are going to delete this. Where can you attach this? What is the possibility? So if you think, you will see that instead of this node, if you directly put this attachment here, it would work, because let us say this node is even having more children and maybe there is a complete subtree below this. Still, all these values will be lesser than the root. This condition will still hold because it is a binary search tree. We know whatever be the values in left subtree have to be lesser than the root, which means all these values which are in the right subtree of the node to be deleted, whether it be right or left, whichever subtree, they are surely lesser than the root. You know this by default. Because of this, whenever you want to delete a node with one child, what you can do is you can simply remove this attachment and attach the complete child subtree to the position where the node was present. So what you will do, you will take this child subtree and attach it here. Then your problem is solved. So let us say this node is present, this is also present. If you want to delete this child will come here, it will be placed here, and you will remove this part. So this is how you will remove a node with one child. This is still okay. The complex part is when you have two children, okay? So this is about removing when you have one child. What if you have two children? That is when things get complex. So let us see what if you have two children. If you want to remove this root, what will happen? It is having two children. One is here, one is here. Whenever you have two children, you want to make sure that the binary search property of the tree is not disturbed. And you want to remove the node which is having two children. So here either of these, this node or this node, both of these are having two children. If you consider this node, if you take this node off, you should find some way of attaching the left subtree as well as the right subtree. So you can't do what you did previously. In the last situation, what we did is we attached one subtree directly to wherever the deleted node was deleted, because there was only one subtree present. But in this case, you have two different subtrees, so you can't attach both to the same position. What are you going to do? What you're going to do is, you won't delete this node off. Instead, you will replace the value of this node with some node from its subtrees, and then you'll remove the node that is holding that value which you substituted. So what you are going to do is, you have to find the right value that can sit here. What can be the right value that can sit here? Consider there is a complete left subtree here, complete right subtree here. You want to pick either one node from the left subtree or one node from the right subtree that is the best suitable node to be placed here. So there are two options for you here. One is to pick a node from left subtree. Other option is to pick from right subtree, and both are correct. You can go for both methods, both are right. Then the question is, which node from the right subtree and which node from the left subtree? Answer for this is, logically, what is the condition here? All the nodes in left subtree will be lesser than the root, and all the nodes in right subtree will be greater than the root. This is the condition for following binary search property. So if this property should not be violated, whichever be the value that is coming here, that should be such a value which would be greater than all the values remaining in the left subtree and lesser than all the values remaining in the right subtree. This should be the condition for that node. So what will be that node? It should either be the largest value present in the left subtree or the smallest value present in the right subtree. In both these cases, these conditions won't be violated. Why? Because in left subtree, all the values are lesser than the parent. So if you pick the largest among all those values to become the parent, still the remaining values in left subtree will be smaller than the parent. And what about right subtree? Right subtree is already greater than the parent, and you are picking some node which is lesser than the parent, and hence the right subtree will also remain larger than whatever is the new parent. This is the logic. So what are you going to do? You can either choose the largest value from left subtree or the smallest value from right subtree. So these particular node values, they have a terminology. The largest value in left subtree, it is called in order predecessor, because we know that in a BST, whenever you take in order traversal of a BST, you'll get it in ascending order. It will be ascending order sorted list. This means in order predecessor means the value which would come just before this node in order traversal. That would be the node which is just smaller than this node. And what about the node in the right subtree? If you are picking the largest node from right subtree, that node will be called as in order successor. Why is it called in order successor? Because whatever nodes are present in right node are larger than the present parent, and the node which is having smallest value in the right subtree will be the node which is having the value just higher than whatever is the value of present parent. That is, if you take in order traversal, if this is the parent node, next node to be traversed will be the smallest value in right subtree. That is why it is called in order successor. Whichever node comes just after the present node in order traversal is called in order successor. Whichever node comes just before the present node in order traversal is called in order predecessor. So you can pick either the in order predecessor or the in order successor in order to replace parent node. Once you replace the value of parent node with the in order successor or the predecessor, what is the next step? You have to remove in order successor or predecessor, whichever you substituted here, you want to remove that node. So whether it be from left or right subtrees accordingly. So what we'll do, we'll take an example and just understand this logic. After that, we'll write the pseudocode and find time and space complexities. So as example, we can take 50, then you have 21, 74. Let us say you have 15, 32, 63 and 80. If this is your binary search tree, and you want to remove 32. Leaf, if you want to remove, it is simple. This is the first case. You can simply remove 32 off. There is no problem in it. What is the second case? Second case is if you want to remove a node which is having only one child. Let us say there is a node here with value 28. If you want to still remove 32, what do you have to do? In this case, you have to, when you are removing 32, you have to bring 28 to the place of 32. So 28 will come here. What if 28 still have more children? If let us say 28 is here, it has even more children, maybe 3. Sorry, 3 can't come here. It should be greater than 21, lesser than 28. So it should be 25 here, and whatever should come here should be greater than 28 but lesser than 32. So it can be 30. So if this is your BST, in that case, if you are removing 32, what will happen? This complete subtree will come and sit in the place of 32. So 28 will come here, then you will have 25, 30. This is how it will work. What if you want to delete a node which is having 2 children? This is the question. So if you want to delete 21, 21 is having 2 children. So you have two options. One is to remove the in-order predecessor from the left subtree, or in-order successor from the right subtree. So here in-order predecessor is straightforward because you only have one node. So you will simply do that. What we'll do, we'll try to get the in-order successor from the right subtree. So in-order successor means whichever node is having the smallest value from the right subtree. How will you find the value with a node with smallest value? You have to go to the right subtree and then move as left as possible. It's as simple as that, because you know whenever you move any step towards right, you are going to increase the value. But whenever you move any step towards left, you will decrease the value. So whenever you reach the subtree you want to find the successor from, that is the right subtree, what should you do? You should keep going towards the left. Do not stop till you reach the end. So whenever you reach a leaf, you can stop. Till that point, keep going towards the left. So here 25 is the value. What will you do? You can remove 25 from here and keep here. It would still work because all the values in right subtree will be larger than 25, because 25 was the smallest value from this right subtree. And you know whatever is there in the left subtree is by default smaller than values in the complete right subtree. So that is why this logic will work. Next thing is we want to write the pseudocode. So how can we write the pseudocode for this? For writing the pseudocode, first we should have the logic in mind. In case of leaf node, you can simply delete. In case there is one child, whichever be the child subtree, you have to put it here in the place of the node that you are deleting. In case there are 2 children, then you want to either pick the largest value from left subtree or the smallest value from right subtree. So this is what we are going to write in pseudocode. How can you write this pseudocode? Let us say you want to delete node in BST. So BST delete. I'll call this function as BST delete. In this function, what should be the? You should give root as input and you should have a key, let us say k. K is the value you want to check. Whichever node is having the value k, you want to delete it off. What will you do first? First you will check whether there is root at all. If there is no root at all, that means your tree is having no elements. So you can do nothing, just return null. So if root is null, what can you do? You can't do anything. The only thing you can do is return null, saying there is no deletion possible. What is the next case? Next thing is first thing is you want to do the search algorithm to reach the node which is having this value k. So you want to keep searching in this tree starting from the root at whether you can find the value k or not. So how can you check this? You can have to start if key, that is your value k, if that is less than root pointing value. In that case, what will you do? If you are in the root node, you found that the value you are searching for, in order to delete that node, if that value is lesser than root node, you have to search in the left subtree because it will be present somewhere in the left subtree. What will you do in this case? In this case, you will do root pointing left root pointing left is equal to BST delete. BST delete is I'm going to recursively call it so that it happens recursively in the left subtree of what should be the value now? I should pass root pointing left and then the value k that is to be searched for. So why am I doing this? Why am I returning that value to root pointing left? What I'm going to do in this recursive algorithm is whenever I find the node to be deleted, if it is a leaf node, I'll simply delete it off. So consider you are hitting the leaf node case here. In that case, if you reach the final node in this step, what will happen? If you simply make it null, then your root pointing left will be null. That is, if you're presently at the parent, then you went to the next node, and let us say this node is having the value, and if it is null, if it is a leaf node, then you can simply delete this off. If you make this pointer as null, then you will delete this node off from the tree. That means your deletion is done. So that is what I'm doing here. I know the value is at root pointing left. So whatever is to be done, I'll recursively do in the left subtree. So that is why I'm returning the value to the pointer which is pointing to the left subtree. Okay. Next step is the same thing I have to do with the, in case it is to go to the right subtree. So else if, what should I check? If key is greater than root pointing value. If key is greater than root pointing value, what should I do? I have to go to the right subtree. So in the right subtree, I have to recursively go. So I'll do root pointing right is equal to BST delete of, I should pass root pointing right, that is the right subtree, and then the value k that is to be searched for. So these are the two cases which I will do in case root is not null. So there is a third case where the key is equal to value. We are going to do that. But if root is not null, there is some value, some node is there. First you will check whether the value is lesser or greater than the node. If it is lesser, whatever delete process you are doing, you will recursively do it in the left subtree. If it is greater, then whatever delete process you want to do, you'll recursively do it in the right subtree. So this is where recursion really helps us, because it will logically control the whole thing inside recursion. Let us see what to do in case root becomes equal. So that will be my else case. Because in else initial case, I checked k less than root. Next case, I checked k greater than root. So else case is k equal to root, or I'll just write this case so that it stays clear what exactly is the case. Okay. If k equal to root pointing value. So when you are actually doing, you can simply write an else case. I'm writing this so that you clearly see what is the case here. Okay. So if this is the case, what should you do? You have to deal with three different cases here. In case you found the value, one is if it is a leaf, second is if it is having only one child, third is if it is having two children. All these three cases you have to deal inside this. Let us deal the easiest case first. That is, if it is a root, if this particular node where you found the value is equal to k, if that is a leaf node, what can you do? First, you have to verify if it is leaf. How can you verify? You have to put an if condition. If, how can you see if it is leaf? Both the children should be null. That is, pointer to both the children should be null. So, root pointing left is null and root pointing right is also null. So, this is also null. If both root pointing left and root pointing right are both null, this is root. In case both are null, that means left child is also not present, right child is also not present. What can you do then? You can simply return null. If you simply return null, what happens? If you simply return null, what happens is, in the previous call, I'll show you. Here, we would have come from some sort of a call like this. So let us say we came from this call. So in this call, you are saying whichever, no, let us say this is the leaf, you reach this from here. From here, the parent, you made this call. What happens then? You will go to this, you will understand the value k is present here, and then you will see whether there are children for it. That is the check that we did right now. So you found that both the children are null, only no child is present. In that case, if you simply return null, that means here you are returning null, which means you are making root pointing left of parent node as null. That means this connection is terminated. So you are removing this node from the BST. This is the logic. So let us continue with what we were doing. So here we first already did the case in which there is leaf node is to be deleted. Next case is the node that you want to delete is having one child. How do you deal with this case? In this case, what do you have to do? If it is having only one child, whichever be the child, that should be attached at the place where the node is presently present. So first question is, how do you detect if it is having only one child? So if it is having only one child, other child pointer will be null. This is how you detect that only one child is present. And when you detect that any child's pointer is null, that is one child's pointer is null, what should you do? You should attach the other pointer to the place where node is present. This is the logic we are going to right now. How will you do this? First, you have to identify, that is if you are checking whether, let us do it left child first. Root pointing left is null. So in this case, so you already checked whether it is leaf. You know it is not a leaf. So if it is not a leaf and left child is null, that means right child is present. That is confirmed. So what will you do in this case? You will return right child. You will return root pointing right. Root pointing right. So when you return the right child, how will this logic work? How will the whole right subtree get attached to the previous node? Because again, the same reason that we discussed previously, the call will be coming from here or here. That is, either of these will be the call from the parent. So this is, let us say this is the parent. This called your node. Your node is having the value k that is to be deleted. It doesn't have a left child, but it has a right subtree. Complete right subtree is present. What are you doing from here? Call came from here. Here you identified that only one child is present. So you found that left child is null. So you simply returned pointer to the right child. So you returned this pointer which is pointing to right child. What will that do? It will return this pointer here. And this function is called by the parent. So parent gets the pointer which is pointing to the right child, this pointer. So instead of this, parent's left pointer, that is this root pointing left here, it will be directly given the pointer which was pointing to this right child of the node to be deleted. So this whole thing will come and get attached here. This is what is going to happen. So let us go back to our code. So we did it for the left child. We have to do same case if it is not having a right child. That is, when it is having only one child, there are two cases present. Here we consider that it is only having right child. It is not having a left child. Then you attach right child. And in the present case, what should you do? In the present case, in the next case, what should you do? Else case. Else. Again, I am writing else if case. Else if root pointing right is null. If right is null, that means this particular node is not having a right child. But you already know it is not a leaf, which means it is having a left child. What will you do? You will return root pointing left. So when you return root pointing left, whatever is in the left subtree, that will be attached to the point where this deleted node is present. So this much is the code for removal of a node which is having only one child. Next case is the difficult one, which is removal of a node that is having two children, both the left and right children. In that case, you have to be cautious because you can't delete off the node. That is the point. You can't delete that node off. Instead, you have to take the value of either the largest value from left subtree or the smallest value from right subtree. You have to substitute that value here, and then you have to go and delete either the largest value of left subtree or the smallest value of right subtree, whichever you used here. That node has to be deleted. So deletion will be done at that node, either the in order predecessor or the in order successor. That is what you're going to delete. You're not actually going to delete this node. Here you are going to substitute the value. By changing the value of this node, you will put the value of this or this. This is what you have to do. So in our case, what we'll do is we'll do for successor. We'll do for in order successor. In order successor means largest value from the smallest value from the right subtree. We are going to take smallest value from the right subtree and substitute. So you can look at this algorithm that we are writing, and you can do for in order predecessor as well. So let us start this. So the condition, first thing, you have to identify. So at this point, if it is crossed, you already know it is not a leaf. You already know it is not having single child. So it is having two children. You already know that. What are you going to do? First thing, you have to find the successor, right? So in order to find the successor, let me call it as S. Okay, S is my successor. So I have to find successor using some function. I'll call it find successor. Okay, find successor function. What will I do? I'll directly give it the right pointer, because successor is to be found from the right subtree. I know this is the value to be deleted. So I know the successor is to be found from the right subtree. So for the successor function, I'm going to directly give the pointer to the right child. Okay, not the pointer to this node. So I'll give root pointing right. This is the pointer to the right child. I'll give pointer to right. So what should this find successor function do? This find successor function should go to your right subtree. It will move as left as possible and find the smallest value possible from the right subtree. So this function will return whichever is the smallest value from right subtree as in order successor. So we'll write this function, but first let us assume this function is there. It is giving the value, and you already have the successor here. If you have the successor, what should you do then? You should substitute the value of successor in the value to be deleted. So your root pointing value should be substituted with what? Successor pointing value. Whatever be the value of successor, that should be put in root pointing value. What is the next step? You know you got the value of successor. Once you got the value of successor, you have to delete the successor and not root, right? In this case, we are going to delete the node which is holding in order successor. How will you delete? You will do root pointing right, because the change that you are going to make is in the right subtree. In the right subtree, you are going to delete the successor off. What will you do? You will call the same bst delete function. Bst. So this is a main delete function. We are going to call this specifically in order to delete the successor off. So what will you do this? You will not call this on the root of on this actual node. Instead, you will call in the right subtree. So root pointing right. On the right subtree, you will call it. And what is the value to be deleted? Value to be deleted is not k. This is important. You already substituted the node with k with the value of successor. Value to be deleted here is the value of successor. So successor pointing value, whatever be the value of successor. What will this function do now? This is going to the right subtree of the node with value k. The right subtree, it is going to go here, find out the successor and delete it off. You already took the value of successor. So now you can comfortably delete off the successor. Okay, so at this point, you already deleted the successor. So you have completed all the steps. What can you do? You can return. Return. What will you return? You'll return root. So let us just go through this function, then we'll write the function for finding the successor, okay? So in this function, what we did is bst delete function. We first checked whether the root is null. Then in case it is null, we'll simply return the value null because nothing can be deleted. If your root, there is no tree at all. The root is null, there is nothing to be deleted, return null. Otherwise, what will you do? If k less than root pointing value, then you want to, whatever deletion process is to be done in the left subtree. So you will recursively go to the left subtree. You will make recursive call to left subtree. If it is larger, then you will recursively call the right subtree. After that, what did you do? After you made recursive calls, you checked the condition in case it is equal. So this is the condition in which you want to handle three different types of deletion because you found the value node to be deleted. So you can handle deletion. How will you handle? In case it is a leaf node, that is both the left and right subtrees are null, then you can simply return null because there are no complications. In case it is not a leaf node, it is having one child and the child it is having is right child, that is left child is null, which means right child is present. So you will simply return right subtree. What if the child present is left child, that is if right child is null, you will simply return left subtree. Next thing is, in case none of these cases are hit, then you are aware that the case that is hit is where you are having both the left and right children. If you are having both, then what do you have to do? We are finding in-order successor. You can also go for in-order predecessor. So in order to find the in-order successor, you wrote a function find successor. This is going to find in-order successor from the right subtree. And whenever you get the in-order successor, you will store it in the value s. S is the pointer holding successor now. You will substitute the value at the value node to be deleted with the value of in-order successor. After that, you will delete off in-order successor node. This is the logic. Next thing is, let us write this find function, find successor function. So it will be complete. Our complete pseudocode will be complete then. Find successor from root. Let us say you want to find this successor from this tree. So here, keep in mind that when you are getting this, you are already getting the pointer to the right subtree. So you don't, that's the reason I'm stressing on this is, if someone simply asks you to write a function in order to find the in-order successor, first step is to go to the right subtree, not simply going towards the left. Here, we are already passing the pointer to the right subtree. So because of that, in this function, we can simply move towards the left and find the least value possible. If someone asks you to find in-order successor of this node, first step is going to the right subtree and then you have to go towards left. So here, whatever you are going to get, that is already a pointer to the right subtree. So in this function, we'll be simply moving towards left, okay? So if this is the case, what do you want to do? You want to move towards left till you find the least value, that is the leaf node towards the left. You want to find which is that leaf. See, whenever you reach an in-order successor, it will either be a leaf or it will have one child. When can it have one child? If this is your right subtree, either when you go like this, you'll reach a leaf. Otherwise, you'll reach a point where it can have a right child. It can have right child and complete right subtree here, but this won't have further left child. That means whichever values are going to come here are all greater than this. So you know this is the smallest, right? So your in-order successor will either be a leaf or it will have one child. So in that case, you simply have to go left until there is no more left child. This is the logic we are going to use. How can we write this? First you want, let us say, some current pointer. This current pointer will store whatever is your present value. So root, let us say. What will you do then? You have to have a while loop which will move till there is no more left. So while current should be while current pointing left. So till the point there is a left child, you have to continue this loop. In this loop, what should you do? You should continuously go left and left as possible. So current is equal to current pointing left. What are you doing here? You are updating your current to the left child. This is what you're doing. So when will this come out? This will come out whenever you no more have a left child. And then what will you do? You will return current. So when you return current, what happens? You will get the value of in order predecessor in the, that is, when are you coming out of this loop? When you don't have a left child. So you came like this, and you know this point, you no more have a left child. Left child is null. So you will come out of this loop. So whenever you are out of this loop, whatever be the value in current, that is the in order successor, right? That is the smallest value present in this right subtree. So you are simply returning this current. So this is what will get returned here. So here you will get a pointer pointing to the in order successor. So this completes our logic. Next thing is we have to discuss about time and space complexity of our algorithm. So what are the time and space complexities? First thing you have to understand, in the delete process, what are we doing here? We are trying to find out the node by going as low as possible in this tree. That is in the worst case. Worst case, you may find the node to be deleted in the lowest point. If you find at the root, well and good. But in the worst case, you may find the node to be deleted at the lowest point. So one part is searching till the node. So that you understood till that point that we want to reach, till the point you are searching. So this may take worst case order of n, because in the worst case, the node to be searched may be a leaf. Next thing is, in case of leaf that is 0 children or 1 children, remaining operations are order of 1. You don't have anything to do. But in case of 2 children, then you have to again find successor. So finding successor is again an order of n. But the point here is, you are going to find successor by further going downwards. So if you see the whole process, in the whole, you are only going one time from the top of tree root till the lowest possible node in the worst case. So in worst case, your time complexity will be the height of tree. So what is the height of tree? Height of a binary search tree in worst cases order of n. So your time complexity, worst case time complexity is order of n. What about the space complexity? Whenever you have a tree and you are using recursion for going down the tree, your recursive stack will take up space which is equal to the height of the tree. That is in worst case. So space complexity will also be order of n. And as we discussed in the previous lectures, if you want to decrease the space complexity, you can go for iterative approach. In that case, your space complexity will be order of 1, right? So for the algorithm we have written, it is recursive. So time complexity is order of n, space complexity is order of n. But in case of iterative algorithm, you can take it down to order of 1 space complexity. Time will still be order of n.